Hi, and welcome back. This is lecture 2 of 3 for chapter 4. Now, during the last lecture, I walked you through solving two-dimensional problems. As we noticed, you treat each independent coordinate system as a one-dimensional problem, and they're coupled by time. So, for this lecture, I'm going to solve a number of problems just to sort of show you how this works. The more you do, the easier it gets. So, that said, this is the first problem I'd like to look at. So, in this problem right here, you have a baseball that's thrown horizontally off of a rooftop of a building. We know how high the building is, it's 25 meters, and the baseball is thrown with an initial velocity of 22.4 meters per second. I want to know how long it takes for the baseball to hit the ground. I want to know what the baseball's velocity upon impact is going to be, and also how far away from the base of the building that the baseball travels. So that said, let's draw us a little bit of a picture here. So let's pretend that this right here is the rooftop of your building. Down over here somewhere, this is the ground like that. Okay. So if this is the rooftop, and let's just sort of add a little bit of texture to it, I guess. Oh, lines are on. That's fine. There's the ground like that. Okay. So anyway, if this is the top of your building, I propose that we put our coordinate system's origin there because that's where our baseball is going to be thrown from. So there's that. So here is the y-axis, here's the x-axis, here's the origin. We know the building is 25 meters high, so the height of the building, which would be, we'll say this right here. This is the height. It's 25 meters. Now, also know that this thing is being thrown horizontally. So what that means is that you're throwing it straight down the x-axis. That's your initial velocity. So it's going to be something like this. That V naught is 22.4 meters per second with an angle of 0, which means that V naught y is 0. And in truth, what we've really been given here is V naught x. It only has an x component initially. Now, we expect the ball to immediately start to drop the minute it leaves the person who's throwing its hand. And it's going to make some sort of parabolic fall like this. Let me see if I can fix this part of the free-handed half a parabola I'm making. Something like this, and hits the ground down here. And so this would be our range for the problem, or the distance that this thing travels along the x direction. Right here. It's one of the things we have to find. There's our range. And when it hits the ground here, it's going to have a velocity down like this, we'll say. And I'm going to call this angle again alpha. Here's our final velocity. And we know that this is the shape of the path that's being taken because as this ball travels, it's experiencing free fall. So remember, free fall means that you only have one acceleration, and that is the one due to gravity. Now, that said, I'm going to write our acceleration, oops, I did that, as minus g y hat. Now, why? Well, in free fall problems, as I've mentioned before, the letter g is sort of a placeholder for either 9.8 meters per second squared or 32 feet per second squared. You'll notice that there's no negative sign here. G is just a constant. It's just a value, and we have applied the direction by putting a minus sign out in front of it. This is actually a common mistake that I see made by students. As I've mentioned before, not squaring things like time or velocities or things like that whenever you're doing a calculation is one common mistake. The other common mistake is putting in minus 9.8 for g. It's not. It's just a number. Like I said, the negative sign is the directional aspect of it. So we're going to do it this way, though. There's a reason for that, and you'll see why later on. So this seems to be about all the information that we've been given. Okay. I will note the fact that our initial position in x and y is 0. So we can put that here if you want. And so let's just fill in our givens and what we're trying to find here. We are given that our initial velocity in the y direction is 0. That's because it's being thrown horizontally. Horizontally means straight down the x-axis. We're also given our initial velocity, which is the same as our initial in x, is 22.4 meters per second. We know our acceleration in x is going to be 0 because this is free fall. Our acceleration in y is going to be minus g, or minus 9.8 meters per second squared. All right. We know our initial position in x is the same thing as our initial position in y. That's going to be 0. But we also know as this thing falls down and hits the bottom here, that the final position in the y direction, which is just y, is going to be 25 meters below the origin. So here, we're going to write it the following way. Minus 25 meters. 25 meters below the origin. All right. Now, let's see. Do we have anything else? I think this is about it. Yes. So what are we trying to find? Well, pretty much everything else. So we're going to need to find delta x. We're going to need to find the velocity upon impact. And we're going to need to find the amount of time it takes for it to fall. Okay? So pretty clear is what's going on here. Next thing you do is what we always do, and that's write down our equations and see if they simplify a little bit. So I'm going to make a little bit of space there. So we're going to have our equations in the x direction. We'll have our equations in the y direction. So in x, I have v is equal to v naught x plus ax times t. I also have x is equal to x naught plus 1/2 ax t squared plus v naught x times t. I also have v squared x minus v naught sub x squared is equal to 2 times ax times x minus x naught. Okay. In y, you have vy is equal to v naught y. Oops. There we go. Plus ay times t. You have y is equal to y naught plus 1/2 ay times t squared plus v naught y times t. I also have vy minus v naught y squared is equal to 2 times a sub y, y minus y naught. So there are my 3 equations in x and 3 equations in y. Now the x stuff looks really familiar. We already know, because there's no acceleration in the x direction, that all of the acceleration aspects are going to go away. We also know our initial position in x is 0. So again, out of these 3 equations, really the only one that's useful to us is the one that relates to range, which is that one right there. Now in the y direction, we know our initial velocity in y is 0. So anytime you see a v naught y, you can mark that out. That's 0. We also know we're starting at the origin. So that goes away, and that goes away as well. And I think that's about it for simplification here. Okay. So If I were to take and rewrite these equations down here, Vy is equal to minus g times t. See what I did? For Ay, I'm putting in minus g's. Y is equal to minus 1/2 g times t squared. Okay? Vy squared is equal to minus 2gy. All right? Now, so there we go. What are we trying to find? Again, displacement, final velocity, time. Okay. I would like to point out one thing before we get really started here, and that's that we already have one of the components of the final velocity. Remember, the acceleration in the x direction is 0. So what that means is that our ball is always going to travel to the right at 22.4 meters per second, always down the x at that speed. Now, what's changing here, obviously, is your velocity in the y. So we're going to need to find that, since we already know what the x part is to find out final velocity. So let's see, where should we start? I don't know. Why don't we start with time? So I'm going to use this equation right here to find the amount of time it takes for it to fall and hit the ground. That is y is equal to minus 1/2 g times t squared. I'm going to go ahead and solve for t. T is going to equal to the square root of minus 2 times y over g. If you plug the stuff in here, let's see, that minus 2. Now y, remember, is where we end up, and that's minus 25 meters. 25 meters below the origin there. G is just 9.8 meters per second squared. The negative here cancels out the negative here, giving us a positive opponent of the radical, which is a good thing. And let's go ahead and do this calculation here real quick. Let's see. The square root of 2 times 25 divided by 9.8 is 2.26 seconds approximately. And that's about right. If you think about this, you're 25 meters above the ground. As you fall, well, that's about right. Okay. Okay, so here's time. Let's just check that off our list and write it down over here. 2.26 seconds. Next up on the list, why don't we find, I don't know. Why don't we find the displacement in the x direction? It's this one right here. So x is equal to v naught x times t. V naught x is just 22.4 meters per second. T we found out to be 2.26 seconds. So if you do this, uh, 22.4 times 2.26, 50.62. So 50.62 meters is the range, approximately. The last thing is velocity. Now, we already have the x part, like I said. As this thing hits the ground, the x part is going to be unchanged. What's happened here is that it's gained acceleration by falling, or not gained acceleration, but gained y part of velocity by falling here. So we need to find Vy. We could use this. In fact, I propose we use this to find it. Vy is going to equal to minus g times t, or minus 9.8 meters per second squared, times 2.26 seconds. Now, 2.26 times 9.8, 22.15-ish about. So minus 22.15 meters per second approximately. Which makes sense because it's falling down, so it's going to have a negative part on it. So that said, we have the y component. We have the x component up here. Let's go ahead and find the magnitude and the direction of the velocity. So let me draw a little coordinate system here, like this, showing sort of where it impacted, like that. Here is the vector going down into the ground like that. Here's our angle alpha, which we need to find. And let's see here. So if you think of this right here as being the y part of the velocity, and this right here as being the x part of the velocity, like that, then sine of alpha is opposite over hypotenuse. Cosine of alpha is adjacent over hypotenuse. And tangent of alpha is opposite over adjacent, like that. So, let's go ahead and find v using the Pythagorean theorem. Then the square root of Vx, which was the same thing as V naught x, 22.4 meters per second. Go to square that. And then add in the y velocity that we just found, which was minus 22.15. It looks a lot like it's going to be at about, well, I don't know, we'll see. I'm guessing the angle is going to be about 45 degrees, but we'll see. Okay, so what's our velocity here? 22.4 squared plus minus 22.15 squared. And I get 31.5 meters per second. So that's this magnitude. Now, what about the angle alpha? Well, you get it from here by doing arctangent. So the inverse tangent here is Vy over Vx. Let's see, Vy was minus 22.15 meters per second. Vx we found to be 22.4 meters per second. And when you do the inverse tangent of this, let's see. $44.68 degrees. Like I said, really close to 45. In fact, when we're done rounding to sig figs, it's going to be 45, I believe. Yeah, so take a look here. In terms of what the answer is, how long does it take for the baseball to hit the ground? Well, just looking here, I see 3 sig figs here, 2 sig figs here. We're going to have to round it to 2. The time we got was 2.26 seconds, so about 2.3 seconds. How long? 2.3 seconds. Okay. What is the baseball's velocity upon impact? Here, that's a minus, by the way. I see it is 31.5 meters per second. That rounds to 32. 32 meters per second, making an angle of, after rounding to 2, 45 degrees below the x-axis. Okay. So there's that one. How far away from the base of the building does the baseball travel? That's this right here, rounding it to 2 sig figs, 51 meters. Okay, so there you go. An example of a two-dimensional problem dealing with projectile motion. Now, one thing that may not be so obvious to you that I'd like to point out is that this is nothing more than the second half of the projectile motion problem that we worked before. So if you know the first half and the second half, you can connect them in all sorts of ways to get you solutions to these sorts of problems. So next up, you have an arrow that's shot from the top of a hill that's 25 meters high. If the arrow has an initial velocity of 65 meters per second and it's launched with an angle of 35 degrees above the horizontal, how far from the base of the cliff does it travel? Okay, so in this example, we have an arrow that's shot from the top of a hill. The hill is 25 meters high, and the arrow has an initial velocity of 65 meters per second, and it makes an angle of 35 degrees above the horizontal. So what we want to know is how far from the base of the cliff that this arrow is going to travel. So here's what I'm going to do. Let's just sort of freehand kind of a cliff here. So here's a cliff, or a hill rather. Maybe here's the top of your hill, going down to the bottom like that. This right here is going to be my initial position. So this is where I'm launching my arrow from. I don't like how that looks. Let me see if I can fix that. Do it this way. Here we go. Of course. Let's do you again. There you go. All right, better. Excuse me. So, and there's that right there, X and Y. And then here is, the bottom of the hill, ground zipping off like that. So here's Y, here's X. Oh, I see. It's Y and X. And here is our initial velocity. It has a magnitude of 65 meters per second, and it makes an angle of 35 degrees with respect to the horizontal, the x-axis. So we know as we fire this arrow that it's going to go up, hit a peak, and then it's going to fall back down like this. Hitting the ground, something like that. So here is your final velocity right here into the ground like that. Let's see here. It's got an acceleration due to gravity down like that. So again, I'm going to be consistent with my notation, minus g y hat. We had a discussion about that last time. This right here we'll say is the peak, where your velocity in the y direction is 0. But again, our acceleration here is strictly free fall. So what that means is that AX is 0, right? So you have part 1 and part 2, and the range, which is how far from the base of the cliff we're looking at. We're going to pretend the base isn't way out over here. It sits right up under here where things are being shot from. This is just sort of a embellishment, I guess you could say. But really, this is the base. So this is the distance that we're looking for right here. So the whole goal of the problem here is to find the range. Now, if we did know how far out this cliff's, or not this cliff, but this hill extended, then, we could subtract that from the range, and that would give us how far away from the base. But like I said, we're just treating this as though it's a sheer drop. Okay, so let's see. I think that's pretty much all the information that we have. We're starting off from the origin, obviously, so x naught and y naught are 0. We do know that our cliff has a height, or I keep saying cliff, but our hill has a height. Like this right here is 25 meters high. Like that. I think that's about it. So what I propose we do is to take the approach that we did, not in the last problem, but the problem before that, and that's break it up into two pieces. We'll find time for part 1 and time for part 2, and then using the equations that we get for x, we can find delta x1 here, delta x2 here, add them together, and that'll give us how far from the base of the cliff that it travels. So again, you have a two-part problem here. So I'm going to draw my parts out here. Part 1. Going up to the peak like that, where we have a final velocity of 0. This is just part 1. We're going to have to break our velocity up into pieces. It was, 65 meters per second, making an angle of 35 degrees with respect to the x-axis. And, again, we know x naught and y naught are 0. And so what I propose again that we do is to find the time it takes for it to get up to here, and then find the time it takes for it to fall and hit the ground, and then go from there. Using that to find the stuff we're trying to find here. Okay, so really, what have we been given for the first part? Vy is 0, x naught and y naught are the same, they're 0. We have, our acceleration due to gravity, minus gy hat. So ax, again, is 0. Ay is minus g, or minus 9.8 meters per second squared. We have a velocity, initially, of 65 meters per second, making an angle of 35 degrees with respect to the x-axis. Now, we're going to have to break that up into pieces, but we'll get to that here in a moment. The second part has us, starting from the top, we'll say, of the flight, right here. And then falling down from there to hit the ground like that, right? So for this one, this is y-axis, this is the x-axis. We're going to end up down here, a total distance of however far it is above the cliff we go, plus, or the hill, plus the height of the hill. That's a really bad line. So we have the height of the hill right here. So this right here is going to be the total distance that we go below the y-axis. And what that tells us is that we're going to need to find how high above the cliff we go from part 1, and then add that to the height of the cliff, or the height of the hill, and then, note the fact that that's this far down in the negative y direction. So we have a minus y displacement. So we're going to need information again from part one to fill in the initial stuff for part two. Now, we're going to need to find this right here, this distance. So this distance right here would be the range for part two. For part one over here, it would be this distance right here, basically. So this right here would be the range for part one. And adding those together should give us the total distance from the base of this hill. And, again, let's go back over here and just continue filling in stuff for, part two. Again, the only acceleration that you have present is in y. That's it. We know our initial velocity in the y direction is equal to 0. We also know, because of the fact that we don't have any acceleration in the x direction, that the initial velocity in the x direction is going to be the same as it is the whole time, basically. Right? Okay, so looks to be about it. So what I'm going to do is to, as before, solving problems like this, I'm going to snag this right there, and we'll copy it and then paste it over here on a new sheet, like that. Okay, so this is part one. So really the best way to attack these problems is just to find everything, so you find everything that you haven't been given, delta y1, for example, delta x1, time. I think that's about it. So that said, let's go ahead and break our vector up into components here. So there's y, there's x. This is our velocity vector, something like that. Has a magnitude of 65 meters per second, makes an angle theta of 35 degrees above the x-axis. Noting again that this is the opposite side. The opposite side is, v naught y, and this would be the adjacent side. This would be v naught x right there. So, writing out our trig stuff, sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. We can write down tangent, but it's not useful to us in this particular case. V naught y is V naught times sine of theta, which would be 65 meters per second, making an angle of 35 degrees with respect to the x-axis. V naught x is going to be V naught cosine of theta, which would be 65 meters per second, making a cosine of 35 degrees. There you go. So let's just go ahead and solve this, find out what this is. There we go. 65 times sine of 35 is 37.28 meters per second. 65 times cosine of 35 is 53.24. So there's our initial velocity at x and y. And I'd like to point out here that, even though v naught y is 37.28 meters per second, our v naught x is the same throughout. And that's because there's no acceleration in the x direction. And that's 53.24 meters per second. So we have our givens. We know what we're trying to find. The next step is to write down our equations in x and y. So in x, we have Vx is equal to V naught x plus a times x times t, or a sub x times t rather. This is going to be x is equal to x naught plus 1 half ax t squared plus v naught x times t. This is vx squared minus v naught x squared is equal to 2 times a sub x minus x naught. So that's an x. And y, vy is equal to v naught y plus a sub y times t. Y is equal to y naught plus 1 half ay times t squared plus v naught y times t. And again, vy squared minus v naught y squared is equal to 2 times a sub y times y minus y naught. So let's take and plug in the stuff from our givens that will help simplify. And as we already know, the accelerations in x go away. And really, again, the only useful equation that we get in this particular type of problem, your x naught is equal to 0 as well, is v naught x times t. For the y direction stuff, our initial positions in y are 0. And if you look as well, our final velocity in the y direction is 0, so that's 0. That's 0 as well, which means our equations give us the following thing. V naught y plus ay times t is equal to 0. Y is equal to 1 half ay times t squared plus v naught y times t. And minus v naught y squared is equal to 2 times ay times y. So there we go. We have 4 equations overall. Let's not forget the goal here. The goal here ultimately is to find out the range, right? So we keep on task here, and let's just solve for the stuff that we don't know. I propose that that we aim for time first. So if we do that and use that equation right there, you get that t is equal to minus v naught y over ay, or v naught y over g. So if you plug the stuff that we know here in, it's 37.28 meters per second and v naught y, and g is 9.8 meters per second squared. Again, I want to reassert the fact that g is just a number. It's always positive. The minus is the direction, and we put that in already. So if I do this, 37.28 divided by 9.8 gives me 3.80 seconds to the top. So T1 is 3.80 seconds. Okay. Now, next up, we can find delta x. So for this one, delta x1 is equal to v naught x times t. V naught x is 53.24 meters per second. And the time we just got to be 3.80 seconds. So if you go ahead and do that, (53.24) 202.31 meters. All right, so that takes and checks that off the list. Delta x1, 202.31 meters. Right. So we got the time, we got x. Now let's find y. We have options. We could use this one. I prefer this one. It's a lot less complicated. So if you just solve for y for this one, it's minus v naught y squared over 2 times ay, or v naught y squared over 2g, right? So let's plug in the stuff that we have here. 37.28 meters per second is the velocity in y. 2 times 9.8 meters per second squared. And what do we get here? Just that, divide that by 2 times 9.8, 70.90, or 70.91 actually. So how high above the cliff or the hill does this thing go? $70.91 meters. Okay, so we got a lot of information here. That's good. Solved it in entirety. Now let's look at the second part. The second part was right here. Let me once again snag that. Copy, go down here and paste it in its own place. Put it about there, I think. And I'm also going to snag the stuff that I was given and found over here. So let me do that. So let's copy that. And then we'll paste that here as well. Just to remember that this came from part 1. So this comes from number 1 right there. So what we have here, and let's see here. Let me just go ahead and put this additional bit of information that we have, and that's the height of the cliff. It's 25 meters. Should have put that there anyway. Okay, so here's the problem we're solving now. Now look, here, conveniently enough, we've been given some information, initially at least. We know our initial velocity in the y direction is 0 because, the arrow in y goes up, is pulled to rest through the action of gravity, and then is pulled back down towards the ground. We also know that our x component here of velocity, it doesn't change. It's the same all throughout. 53.24 meters per second. Oop. Okay. Again, ax is equal to 0. Ay is minus g, or minus 9.8 meters per second squared, right? We found from working the first part how high above this cliff this thing went. It was 70.91 meters. We also know the height of the cliff. That was 25 meters. So given that, if you consider our initial positions in x and y for this part to be 0, 0, getting ahead of myself. Here, the final position for y is going to be this far down to the face of the cliff, or the face of the hill, if you will, and then we need to go down further to the bottom. So if you add those things together, you have 70.91 plus 25. So what's that, 95.91? Is this many meters below the cliff, right? Now, what are we trying to find? Well, really, to find this, or to solve this problem, we really only need to find delta x2. But to do that, we're going to need to find the time as well. Now, we probably don't need to find the velocity. We'll see. We may need to. I'm going to put here final velocity in question mark, because again, The goal of this problem is to only find how far away from the base of this hill this thing went, or the cliff. This is the problem. Mixing stuff up. So many cliff problems. But that's okay. All right, so like I said, ultimately the goal here is to find delta x2. So again, you can write out all the stuff you want in x, but noting the fact that our initial position in the x direction is 0, just like y, we can write down that really the only equation that's useful to us from x, because of the lack of acceleration in that direction, is just this. We know that from experience. In y, though, let's go ahead and write our equations out. We have Vy is equal to V naught y plus Ay times t. We also have y is equal to y naught plus 1/2 Ay t squared plus V naught y times t. Finally, we have Vy squared minus V naught y squared is equal to 2 times A sub y times y minus y naught. So let's take and plug in the stuff that we have here to simplify this. Obviously, our initial positions are 0 because of how we chose to do the problem. But we also have an initial velocity that's 0 in the y direction. So this goes away. That's 0. This goes away, and so does this right here. It's giving us from this right here 3 equations that are useful. Vy is equal to Ay times t. Y is equal to 1/2 Ay times t squared. And finally, Vy squared is equal to 2 times A sub y times y. Now, so we really want to find this, but to find this, we need to find this. I would use this right here to find it. This is what we need. We know, for example, how far below our origin we're going, and we know our acceleration, which is due to gravity. So t is going to equal to the square root of 2y over A sub y. 2 times minus 95.91 meters divided by minus g, or 2 times 95.91 meters divided by 9.8 meters per second squared. So 2 times 95.91 divided by 9.8. 4.424 seconds, or about 4.42 seconds. So given the time, now we can find the displacement for part 2. It's V naught x times t, V naught x being 53.24 meters per second, and our time being 4.42 seconds. So, $235.32. Okay, great. So take a look here. We have the range from the first part. We just found the range for the second part. So the total distance from the base of this hill or this cliff or whatever we're calling it now is going to be delta x1 plus delta x2, or 202.31 meters plus 235.32 meters. So if you take and you put that stuff in there, 202.31 plus 235.32, that's 437.63 meters. Now, if I go over and look at my problem, I have 2 sig figs here, I have 2 sig figs here, and I have 2 sig figs here. So at the end of the day, when we write down the range, that is the distance from the base of this thing, it is going to be rounded 440 meters, 2 sig figs. So the range is 440 meters. Okay, so the next thing I would like to introduce is something called the range equation. It's useful in specific problems where things are symmetric. So let me write that up here. The range equation. You only want to use this when you are dealing with a symmetric problem. Okay, so we're going to derive it, and the way we're going to derive it is to work a two-dimensional problem that just is a standard projectile motion problem where you're launching something with an initial velocity of v naught that makes an angle of theta with respect to the x-axis. So we already know that this thing is going to go up, it's going to hit a peak, it's going to come back down and fall down like that. We don't care in this particular case about the final velocity. We don't care about that. We don't care about the angle of impact or anything like that. What we want to find is just the range. That's the only thing we're looking for. Okay. So in many ways, it's similar to one of the previous problems that we worked. Now, the trick here is that this is symmetric, and we know that when you're dealing with a symmetric problem, there are certain things that you can take advantage of to make your work easy. For example, if I found the amount of time that it took for the projectile to get up to the very top, if I doubled that, so to find the total time, it would look something like that. So the total time is twice what it takes to get to the peak. And we also know up here your velocity in the y direction is 0. We also know, dealing with a free fall type problem like this, that the only acceleration that we have present is that due to gravity. Okay, so once again, our acceleration here, and I want to keep this all symbolic, we're not going to put any big numbers in here, is minus g in the y direction, right? So it's so there's our acceleration. So no acceleration in the x direction. So it's a generic problem, where we're trying to find range basically. We're going to take advantage, like I said, of this. We're all going to take advantage of the fact that range is going to be, twice whatever the displacement is in the first part, right? So that said, our givens would look something like this. Our initial velocity is v naught that makes an angle of theta with respect to x. The velocity in the first part at the top is 0. This is at the peak part. We know the velocity in the x direction initially is going to be constant. If you remember that, this is because of the fact that there is no acceleration in the x direction. But we do know that there is acceleration in the y direction. It's g down, right? Let's see. I think that's about it. And really what we want to try to find here is the range. Okay, so we're only going to work the first half of the problem here, and we're going to use the information that we get from the first half to find the range. So here's the first half. It's just going up to the top like this. Here's our initial velocity. It goes up something like this, like that. It's a sort of pathetic parabola. We're going to go on. We're going to go with that. So up here at the top, it's 0 on Vy. This right here would be delta x1, which again, if we find this and we double it, that gives us the range. Here's y, here's x, v naught magnitude, making theta with respect to the x-axis. Now, finally, a little bit of acceleration here due to gravity, minus g y hat, right? Okay, so our givens, again, look a lot like this. We have our initial velocity, v naught, with theta. We're going to need to break this up into components, which we'll get to here in a moment. We know at the peak, though, Vy is equal to 0, and we know that whatever we get for Vx naught, it's the same thing as Vx, which, is constant. We know that our initial positions as drawn are 0. We know the acceleration in the x direction is 0. We know the acceleration in the y direction is g down. And really, this is about it. So let's go ahead and break our velocity up into components. Okay, there's theta, v naught. This right here, the side right there would be v naught y. This side right here would be v naught x. And, if you think of your standard sine of theta being opposite over hypotenuse, cosine of theta being adjacent over hypotenuse. Symbolically, our velocity in the y direction would be this, up, sine. And our velocity in the x direction would be this. Right? So, given that, let's write down our equations in x and in y. I'm going to draw from information that we already know. That is our equation in the x direction. The only one that's going to be useful to us is this, and that's because the acceleration in the x direction is 0, which makes 2 equations out of 3 just be statements of, yeah, the velocity in the x direction is constant. In y, though, that's not the case. However, in y, we can write this, vy is equal to v naught y plus ay times t, x, or y, x. Let's get rid of that. Y is equal to y naught plus 1/2 a sub y times t squared plus v naught y times t. Vy squared minus v naught y squared is equal to 2 times ay times y minus y naught. Okay, so there's our 3 kinematic equations. And what we're going to do now is to take our givens here and simplify things, noting the fact that our initial positions are defined to be 0, and our final velocity in the y direction for the first part, and again, let's not forget this is just the first part going up to the peak, is 0. So that's 0, that's 0. And so, really out of these equations right here, when we're done massaging them, we end up with this right here. Whoops, let me write that as that's 0. Y is equal to 1/2 ay times t squared plus v naught y times t, and minus v naught y squared is equal to 2 times ay times delta y. Now, all we need to do here is to find the time, and here's why. This is the equation that we have that's going to give us our displacement. If we can find the amount of time that it takes to get up to the top, okay, and we double it, then we can plug it in here and that will give us our full displacement. Okay? Or we can find the amount of time it takes up to get to the top, do this calculation and just double it. It's the same thing. It's the same process. One just doubles position, noting the fact that the first part and the second part would be the same, and one just doubles time. So that said, all we need really is the time. And to find that, I would use this equation right here. It's the simplest one that we have that gives us that. And if you solve for time here, this would be the time to the peak, time to the very top. It would be minus v naught y over a sub y. Now, v naught y is v naught times sine of theta. Ay is minus g. So the time to the peak is v naught sine theta over g. Now, that said, the total time spent traveling is going to be double that. We know that because this is a symmetric problem. Okay. Now, let's plug this time into here to find out what the range is. The range is going to be you traveling at v naught x during the whole problem, the total time. So here, v naught x, we know from up here, is v naught cosine theta. Right? The total flight time is 2 v naught sine theta divided by g. Okay? So what I see here is 2 v naught squared cosine of theta sine of theta divided by g as the range. Now we're actually going to clean this up a little bit. There's the double angle theorem from it's a trig identity that says sine of 2 times theta is what you get when you take and you have 2 sine of theta cosine of theta. And that's exactly what we have here. Okay, so that's sine of 2 theta, which means that we can rewrite our range equation as v naught squared sine of 2 theta divided by g. So this right here is our range equation. That's what this is right here. That's the range equation. All right. Now, to be clear, though, it only works for symmetric problems. Now, you could conceivably derive your own range equation that would work on complicated problems like, for example, this one. We're not going to do that. But you could if you wanted to and you were desperate. Now, that said, let me show you how you can use the range equation. So let me just copy it here. Whoops. It helps if you actually take and highlight what you're trying to copy. We're going to copy it, and let me paste it over here for this problem. So this is a bit of a historical problem. As World War II was starting to come to a close, the Germans actually were absolutely getting wrecked by these tiny little tanks that were Sherman tanks that were fast. Their big tanks could fire at one of these smaller tanks, and the small tank would just move before the round got to it. Germany, though, thought that the best solution was to just make it bigger and better. And so they created this tank called the Tiger II Panzer Kampfwagen. Now, this thing shot a shell with an enormous velocity. As you can see here, 1,130 meters per second. Now, what I'd like to do is to find out what the maximum range of this cannon would be. Okay, so let's draw a picture right here. And we don't know what the angle is. We need to find the max range. That's one of the things we're going to have to decide. We do know the initial velocity of the shell is 1,130 meters per second. Now, we're going to let this fly in its standard parabolic shape, hitting the ground somewhere over here. And obviously, this right here is going to be the range right there. Okay. Now, so this is the range. We need to maximize this. Now, you could make things complicated and do derivatives and all that stuff, Or you could take a look at the equation for range itself. V naught squared sine of 2 theta over g. Now, this is a fixed thing. In this particular problem, the initial velocity is 1,130 meters per second. You can't change that. G is a constant. It's 9.8 meters per second squared. Remember, it's not negative. Okay, we put the negative in when we derived a range equation right here. That's already been taken care of. Okay. So the only thing on the right-hand side that can change that would give you your maximum R would be your angle. So one question you might ask is what angle is this equation at a maximum? Okay. And we know, because of the behavior of sine, since it looks like this, that your peak value of sine happens when theta is at 90 degrees. 0 to 90, back to 0, right? Rather, 0 to 1 to 0 to minus 1 to 0 to 1, and so on. 0, 90 degrees, 180 degrees, 270, 360. So the angle to sine would have to be 90 degrees. So that means that 2 theta would have to be 90 degrees. And what that means is that 45 degrees is the angle that maximizes the range of something that's shot on a flat surface like this. Okay, this is a true statement. Now, if you take and you put 45 degrees in here, 2 times 45 is 90. Sine of 90 is 1, which means that for maximum range, the equation that you're looking to solve looks like V naught squared over G. It's that easy. So if you plug in what V naught is, which is 1,130 meters per second, and you square it and then divide it by 9.8 meters per second, that's going to give you an idea of what the true range of this thing would be like, neglecting things like wind resistance and what have you. So, let's see here. (1,130) squared divided by 9.8 ends up being something like 130 kilometers. Okay, 130,295 meters. More like 296 if you round, actually. Now, to be clear, that's not the actual range of this tank. In fact, if you look this thing up, Tiger 2 Panzer Kampfwagen. Let's see here. To look it up. I used to know it. All right. So this thing right here has a range according to the actual numbers of about 9.4 kilometers. So our calculation says 130,000 or 130 kilometers, but in reality it's this, and that's entirely due to wind resistance. Now, we'll be talking more about that later on. We can't talk about it yet because we don't have the tools for it. But this is a good demonstration to show you the difference between theory and reality. Okay? Now, so this equation is incredibly useful, whether you use this form right here or you use this form right here. For example, I could conceivably tell you or ask you to do a question like this. You want to hit something this far away. This is the velocity produced by whatever it is you're shooting. And what's the angle that's required for you to do that? And you could easily solve this equation and get the answer without having to go through all of this drama right here. Okay. So it gives you options, I guess is what I'm trying to say. Now, that said, this concludes the second lecture on chapter 4. The next lecture we're going to do is going to deal with circular motion. And I'll see you then.